So hello everyone. Welcome to this week's Crunch seminar. Thank you so much for joining us today. Today we have two presentations. Our first speaker is Professor Stefano Zampini. He, as a computational mathematician and software engineer, Stefano Zampini lies at the intersection of numerical analysis, predictive simulations, and high performance computing with recent forays into machine learning. While a theorist by training, he spent his working career in the design and implementation of algorithms for the simulation of physical applications, including electromechanical cardiology, computational fluid dynamics, electromagnetics, geophysics, chemistry, isogeometric analysis, fractional diffusion, and PD constraint optimizations. His contribution to the field of domain decomposition have been recognized by two plenary talk invitations at the International Conference on Domain Decomposition Methods. He's one of the principal developers of the portable and extensible toolkit for scientific computing, which is an R&D 100 award-winning massively parallel framework for the solution of large-scale nonlinear system of equations. His contribution to the open source software community for computational science and engineering extends to widely adopted framework in the US Department of Energy ecosystem for the numerical solution of partial differential equations, namely MFEM, and DEAL2 libraries for finite element-based simulations. He's also a member of the HPC Technical Committee and the CFD software package Open Forum. Stefano, with this short introduction, welcome to this week's Crunch seminar. You can start whenever you're ready.
Thank you. I didn't know that you would have read the entire bio that I sent you, but it was nice for you. So thank you very much. Thank you very much for inviting me and to give me the opportunity to describe and discuss what we have been doing as a research with some of my colleagues in KAUST, namely George Turquia and David Keys. And Umberto Zebbinati, that was a PhD master student at the time that we started this work a couple of years ago in KAUST, and now he's a PhD student in the University of Oxford. So what I'm going to discuss is, some sort of a journey that we decided to do a couple of years ago to try to see what if something can be done from the point of view of the training problem in machine learning, starting from scientific machine learning, because we come from this is our background, computational science and engineering, and try to see if we can improve approximation properties of the learned models if we use what we call conventional optimization solvers instead of the usual fancy optimization solvers that they use for machine learning in general. So, so this is the outline of my talk. Just confirm, I have 50 minutes?
Yes. Ideally, it's 50 minutes for the presentation and then 2 minutes for your questions. But if you need a few more minutes, we can extend it. It's not like a hard constraint.
Okay. Just let me know when I'm in my last 5 minutes or so. So the idea, this is the outline of my talk. I already discussed a little bit the motivation, but give some few points there. Briefly cover what is the deep learning training problem that I guess more or less everyone on this call is aware of, and then discuss some of the fruits of our work, which is a very lightweight software which we call PETSI-ML, which is based on PETSI, which is a library to solve partial differential equations, a large-scale partial differential equation. And that can also take advantage of GPUs, and we use the library to take advantage of optimization solvers to solve the training problem of deep learning. And then I move to some numerical results. So we'll have some results for physics reinforced neural network, some results coming from molecular dynamics, and the late point is on operator learning that contains the results of a paper that recently appeared, where we discuss what I'm going to discuss here and in much more details. So as a motivation, I guess 23 participants on this call, we all work more or less on fruits of what has been the impact that deep neural networks has had on computer vision and natural language processing in the past. And we have been seeing the rise of many computational methods, data-driven methods that now we can, claim they are under the umbrella of, what is scientific machine learning. For example, there are physical informed neural networks that can be used to solve partial differential equations in a data-driven fashion. Blends of more conventional methods and data-driven methods like the deep Galerkin or the Ripritz methods, but there are also methods like, for example, methods to, instead of solving the PDE, solve the operator that maps, one Banach space to the other. So maps try to learn the map between, for example, parameter to observables, and some of the successful techniques that has been presented in the past are in the last few years is DeepONet, FNO, physical informed neural operators, green learning, but there are many others. But here is just to have an idea of the fact that many techniques has come up and constitute some sort of new field for us to test for optimization solvers. So at least in my opinion, whether if all these kind of methods are successful and important, and it's still up to debate for sure. It is those methods provides new tools to tackle high-dimensional problems, and there has been some already some success in the literature where data-driven machine learning inspired methods has pushed the boundaries for some of the very challenging problems. Here I'm just listing a couple. One is molecular dynamic simulations, and another one is solving the high-dimensional HJB equations. On this wave of success, the next step is people still trying to work on constructing foundation models on science, like on the success of building on the success of the large language models and the diffusion models, to try to construct foundation models also for science. So the point that we were interested in is, okay, we want to use this kind of method to do scientific machine learning, so to do predictions. So in some sense, we care about accuracy. So we really care about approximation errors of the models that we learn, in particular when it comes to solve partial differential equations. So the question that we had in mind is, the data set that describes these scientific machine learning problems are peculiar and quite different with respect to the data sets that are instead used in more standard machine learning frameworks. So, for example, you have a great abundance of data because you really want to learn, for example, the operator that maps parameter to solution of a PDE, and you really need as much data as you can to feed to the network to really learn the realization of the network. And so first you have the data is much more abundant, and also the data is smooth. It's not like you're trying to learn the map between an RGB image to the string cat or dog, right? It's the operators that you try to learn are smoother. So with all these intuitions, the question is, can we improve approximation properties of the models if we train them with conventional optimization solvers, or I call it also second order solver like Newton or its derivatives of quasi-Newton. So the first thing that we tried to do was, okay, what's the simplest thing that we can think about is, I want to interpolate a function, right? So to interpolate a function, in this specific example, I'm using a 3-layer dense network. You see D is the input, D is the input of the network, which is in 2-dimensional space or in 3-dimensional space in this case. And I have this is just a toy problem. It's I'm trying to learn actually to interpolate the function. So I want to learn a neural network that for a given set of parameters, approximate the function at some random points that I have. And here in this case, we use 10,000 random points in this domain. And for the three-dimensional, so this is 2D plus time, which is some sort of scattering problem. We use 1 million points in the space-time domain, and this is so those are not really high frequency, but not really slow frequencies. Is they possess some features already that should be difficult to learn, right? So for example, the scatterer is just this this three-dimensional field, right? That this is generated with spherical harmonics, so it has some low dimensional manifold where the simulation, and also this is basically 4 parameters. So yes, can we learn this thing? And the clearly is yes, right? But the point is not can we learn it? Is up to which point? What is the error that we commit, right? So this was the very first preliminary example, but we wanted really to see if there were some difference between using, for example, here I'm using Adam. We didn't do, the great, hyperparameter tree because that was not the point. So probably you can get a little bit better, but this is quite typical, right? So you have to. So coming from not being part of the machine learning community, you always have to face the problem of, oh, I have to shorten my learning rate. I probably should use a different scheduler or something like that. And then things gets complicated and to try to squeeze some more performance. Here instead, the other approximation errors curves that are in terms of iteration of the optimization solver are for BFGS, which is a quasi-Newton method, and using the full Newton method, and using the Gauss-Newton method, which is, I will describe later, a method that similar to Newton, but it takes an approximation of the edge. So as first thing that one can see is that okay, I have 4 order of magnitude in the loss difference. Is this something that translates in also generalization error? And the answer is yes. So this instead, here instead you have the learned solution with 3 different solvers: Adam, BFGS, and Newton, and you can. And those are generalization error, which means that I'm just sampling the neural network in equispace points, and I plot the difference, and you can see that even the order of generalization error is significantly different when using second order methods. So the idea. So this gives us some confidence that we probably should try to do some more serious experimentation and analysis, not analysis, so experimentation and study of using this kind of methods for other problems. So before I show you some other results, so the idea, what is the actual problem that we are trying to solve here, right? We want to learn a function, which I call it y here, right? That goes to some set of parameters, theta, and some, random, some input space, capital X, to, output space, capital Y. So for example, classification, capital Y is the number of classes, for the size of the number of classes. X is, RGB images or something like that. But for scientific machine learning, this can be fields defined on grids or in general, on some semi-structured, set of points. So and the idea is we want to learn the best approximation possible of this function. Okay. So in principle, the best approximation possible. So this is not really mathematics. It's just to have an idea of how the error is split. The best approximation possible between the map of the function and the actual solution that we want to have can be split in what is generally referred to as accuracy error. So how well I can actually represent the output space in general, because X, in general I don't know the entire X. I just know a sampling of X, right? So and then which I call X of T. So then there is how well I can actually learn the data that I'm given to solve the problem, and this is what is called the training error. and this is something that, this is what you bring down with your loss, right? So this is the loss function value. And then you have generalization errors, the fact that, this is the error that you commit on unseen data. So how well, my function knowing, so this is not really math, it's just to have an idea. So is what is the error that I commit to unseen data? And how, mathematically speaking, this problem of learning why, is framed as usual as the average of loss functions defined on mini batches, xi, bar xi, bar yi, those are mini batches. Calligraphically here is, some empirical loss function that you define that you want to that you use as a proxy to minimize the error that you commit between, between the data that you produce and the data that actually you have to match. So this is in case of supervised learning. And you want to minimize the scalar function over some parameter set, or some parameter set theta, and how theta interacts with y is the network. Okay. So in machine learning, what how they solve this problem, because they are in a completely different regimes in terms of data. They use first order methods like SGD and derivatives, which means they sample an unbiased. They have an unbiased sample of the gradient that they call the mini batch gradient, and then they move slowly in the direction of the mini batch gradient, or an adaptation of the mini batch gradient with respect to some rule like Adam, Ada delta, Ada grad, RMS prop. There are many of those methods, but the idea is that the gradient and the history of the gradients tells you where to go, and lambda k is what they call the learning rate, which is how much you move into that direction. So this kind of solvers are great when as I said, you are in data scarce regime and in overparameterized model, because the stochasticity acts as a regularizer, which means that you never overfit, and your generalization error is always quite good. What the main drawback of the methods is that clearly requires hyperparameter tuning, which means how large that has to be the batch size. How should I schedule the learning rate? What kind of method should I use? So the question is why we should use also this kind of method in scientific machine learning is because there is no other way to solve these problems. I don't think so. So the idea is, okay, as usually done in in the optimization community, yes, we still move in some direction, but this direction is not the gradient direction. Is the direction is scaled by the action of the inverse of some approximation of the action. So in all the results that I have, there will also be the exact action that is never computed explicitly, but actually just compute a matrix vector product are computed, but can also be approximations like for quasi-Newton methods, or that use previous histories of the gradients to compute an approximation of the second approximation of the action, or the Gauss-Newton approximation. And clearly lambda k, depending on the method, can be selected using a line search. So instead of just moving slowly into the direction, we will look into the direction pointed by the step, and try to compute the objective that minimize the new objective function. So as I said, okay, so the three methods that I have in this talk, but the idea of the code that we have, that you can use any of the solvers that are available in PETSI, but we will present only a few results. One is for BFGS, which is the next approximation of the Hessian is computed by rank 2 updates. So this is quite standard, and it can be found in many optimization books. And also standard are the Newton method, or the trust region method. For the Newton method, actually this is the approximate Newton method. In the approximate Newton method, what we want to do is to solve in an approximate way, so up to some tolerance, this problem, and this new K here, this is dynamically adjusted and tweaked, so this gets smaller and smaller as Newton gets to convergence, because in the early stage of the optimization, Newton is not even guaranteed to be a convergent method. So, another alternative is to use the trust region method, which is the most successful that we found so far. So the idea of the trust region method is very similar to the Newton method, but we saw the problem that we solve is, from the point of view of the numerical analysis, very similar. But this is called the quadratic model problem of trust region, because we stop as the step is inside what we call the trust region, the region in which we trust the model. So in each step of the solver, we trust, we assume that the model has that we can approximate our fully nonlinear model with a quadratic model. In this case, can be also linear, and we minimize the objective function, if this is the objective function, if the model is linear. And we minimize it only in a region where we trust the model. Okay, and the size of the region is delta here, which is the trust region. And then we move on. And how we decide to enlarge or shrink shrink the trust region is by checking if the reduction in the model, so the reduction in the quadratic model, is aligned in the reduction of the actually full nonlinear model. So here we don't have line search. So the idea of trust region is always to take the full step. So because what tells us how to trust the model is the trust region size. So we compare this, and if this is above 0 and above some floating point value between 0 and 1, we accept the region and we enlarge it or shrink it depending on the value. Otherwise, if this is negative, we shrink the region and we continue. Trust region is guaranteed to converge to a first order critical point, differently from Newton. So, so summarizing, there are clearly many pros about using second order methods. First, they have been validated on a plethora of problems by the optimization community in the last 30 years or so, not only for PD constraint optimization, but in general for optimization problems. When they work, they have framing it in the wording of machine learning. They have a weaker dependence on hyperparameters, which is, for example, for trust region, those are the scalars that I use to say, okay, how much do I shrink the trust region? How much do I enlarge it? Or when I decide, or what is the ratio between model and actual reduction that tells me that this is a good size. So very few hyperparameters.
Stefano, I have a question
also,
here.
Yes, please.
This is George. Can you have mini batching? Because I know in LBFGS we cannot use, but can you use mini batching in? Is that
yes, yes, I have. Yes, all the results that I have here, they are not using mini batching because I was trying to actually match the same configuration used in publications. So I don't want to do anything different, right? But yes, for example, trust region is much more robust than Newton in mini batching, because Newton always tends to overfit, and instead trust region, if you really are careful in how you define your trust region, yes, and actually I can so trust region without hyperparameter tuning can do the same. So for example, in toy problems like MNIST classification with ResNets or CNNs or Cipher10, I can get usually. So for example, for MNIST and CNN, I have an SGD that does 95% and trust region that does 94%. For Cipher 10, I have similar results, something like 90. I remember 93 for SGD and 92 for trust region. So those are very close. Okay,
right.
It's not when you compare against this toy data set, you always compare about hours and hours and months of hyperparameter tuning and tuning on the specific data set. That is very hard to understand if you're actually doing good or not. So is 1% really so bad? I'm not, less. I'm really not sure. But yes, I can tell you that trust region is still good in Bini batching.
Okay. Thank you.
You're welcome. So just to clean, yeah, mini batch trust region works better than Newton. And the other thing is that to really have, depending on that, clearly this is always problem dependent, but larger batch sizes can be detrimental to first order methods. This is always clearly problem dependent. And you have to do something. There are methods that has been designed like, LARS and LAMB that have been designed to work with large batch sizes. But, instead, what I've observed that really, when you do mini batching, the size of the mini batch doesn't impact, very much the convergence. Yes, clearly, full data set iteration epochs are not as good in generalization error, but there is the window in which you can take the mini batch size is much larger, for this for at least for trust region instead of usual first order methods. What are the drawbacks? Clearly, those methods are not very as simple as to be implemented as first order methods, and they possess many different moving parts, right? For example, if I want to use Newton, I really want, I really need a way to safeguard Newton. I really need a way to do line search, but there is not a simple way of doing line search. There are many, so I need to solve linear problems because at every step I have to solve the linearization, the tangent problem. So there are the pieces of software that you need are quite complicated. And that's the reason why we decided to, to interface machine learning backends to Betsy. Clearly, as I said, those methods also have shown overfitting in few regimes that are not the method of choice in machine learning. Also because memory requirements tend to be prohibitive because computing a gradient takes some amount of memory on the GPU, but computing an Hessian, which is the gradient of the gradient, let's call it this way, the memory requirements to store the intermediate, whatever the graph, the machine learning backend does to store the graph, or it's quite the memory requirements to store that thing and operate on that thing are so large that large models cannot really fit on single devices. So one alternative is, instead of doing full Hessian matrix better product, is to do what is called the Gauss-Newton approximation, or the generalized Gauss-Newton approximation, how it is known in the machine learning community, which is, so the Gauss-Newton approximation is usually for nonlinear least squares, and H here is 1/2. So usually you disregard this, but the idea is that J is the Jacobian of your neural network with respect to parameters. And capital H here is the second order is the Hessian of the loss, and J transpose is the transpose application of the Jacobian of the neural network. So why this is memory performant is because basically these are as the memory cost of a gradient, because you just go one time up and one time down the hierarchy, and then you compute the action of the matrix vector product. Is this true? And at least for the problems that I've tried, yes. So for example, if you do, so this was one of the earliest things that we tried is, can we do Gauss-Newton on a ResNet? And this is using Cipher 10. and A100 GPUs, and this is going over the entire data set. So so those are all these holes are because data set is on the CPU. You have to put it on your GPU and everything. But anyway, you can see that I have the data without other data without this kind of noise here. But here you can see that the initial MATVEX is in the full data set is more or less the same time of the gradient data of computing a gradient. So that's why usually when people do second order solvers for machine learning, they don't compare performances of the solvers with respect to time to solution, but on using oracle calls, which means for example, what is an oracle call? An oracle call is is an objective function, okay? Because really what I want to compute is minimize the objective function, right? So I say the objective function costs 1. A gradient costs 2 because to compute the gradient I have to differentiate the objective function, which means I have to go up and down the hierarchy. So compute the objective and go backward in the PyTorch and go backward in the PyTorch Lingo to compute the actual gradient. For the Haoyang MATVEC, as I said before, you actually compute you first compute the Jacobian and then you compute the transpose of the Jacobian, and this is you see clearly go one up and one down, so the cost is 2. For the Haoyang, since the full Haoyang is the gradient of the gradient, is twice the oracle cost of the gradient.
I have a question, Stefano. So
yes.
the Gauss-Newton, is it second order or is like the quasi-Newton, which is like
no okay, Gauss-Newton is so so it depends what you intend by second order. I mean, Gauss-Newton is like Newton and trust region. When they are in the Borel convergence, they have second order convergence because Gauss-Newton is the approximation of the Newton of the actual full Haoyang. So you basically drop one term, and you drop one term that depends on the size of the gradient. So when you are close by to a first order critical point, the term is negligible. Okay, so you can prove that if you are in the first order critical point, the Gauss-Newton matrix is actually the Haoyang, because that term will be 0. Okay, so
right, in practice,
the idea of Gauss.
I was wondering if you actually realize second order convergence also in the experiment.
Yes, definitely, yes.
Because in LBFGS you don't, right? 1.5.
No, you don't. No, never. No, because because it's quasi-Newton, right? You have to have the full history and adapt. No, for this, yes.
But
because the point is that yes, you do it modulo. I show you the results, but yes, you get the same convergence here. Right. So there are other, there is some work recently done on starting from the KFAC approximation on using, quasi-Newton or adapting quasi-Newton methods to the framework of neural networks. I'm not going in there. What the results that I'm going to show you are more aligned instead of the approach by Mahoney and co-workers, which is actually using Newton or with some special choice of linear solver like CG or MinRes or something, and it's more in line with this kind of works. So other questions, or can I go? Are there any other questions, or can I move on? Okay, I move on. So the whole point of doing of this talk is also to discuss that the solver, the code that I'm using is public, and you can run more or less the same experiments, because the code that I made public is the third generation of the code that we've been writing in the last 2 years. So I did import all the numerical results that I have here, but I can, if anyone is interested, I can do it. But there are many demos that you can run that are in the paper that I'm going to discuss later, and all is based on PETSI, which is software for partially designed to solve nonlinear equations, usually root finding problems, or also ODEs in time for partial differential equation. And what the idea is basically that everything is built on top of user callbacks. So PETSI doesn't know anything about, what is the residual of the equation, doesn't know anything how it is, what is the Jacobian of the equation. It just gives callbacks, to the user to say, look, at this point, I really need to sample the residual. Okay, so suppose that I have to compute G. Okay, so what is the residual? It's the gradient for me, right? So can you give me the gradient? Yeah, this has to be, in a linear memory, in a vector, but this is some sort of overhead that we have. But yes, this is, can you populate this vector with the values of the residual? Yes, and then can you actually set up your matrix to do a matrix vector product, and then everything is handled by the library. So blue is user, here inside is the library, so the library automatically knows how to call the Krylov solver, when to stop the Krylov solver, which kind of preconditioner to use it, and this has been validated, in the last 30 years, and it's quite, it's largely used in the DOE ecosystem, but also worldwide. So PETSI-ML is basically a lightweight wrapper on top of PETSI-4.5, which are the Python bindings of PETSI. Is available at this URL here, and the idea is that we really want to provide easy access to optimization solvers using abstract classes for objective function. And the software that we have currently supports JAX and PyTorch as machine learning backends, but others can be supported, And we have also some preliminary interface to DeepXD, because some of the results that I have are for DeepONet. And it supports distributed memory, multi-GPU computation, and as I said, this is third generation of the software, still under development. But if you want to, if you want to use it, it's stable. It's stable because I've been writing code for almost 2 decades now, so the code is stable. You can use it. So how does it work? This is not really how it, but the idea is that you have a function that has to obey some interface, and the interface is very general. Say, give me the value of the objective as some parameter value. Give me the value of give me the gradient, give me the action of the Haoyang matrix vector product. And this doesn't know anything about the numerical backend of PETSI. So this is basically PyTorch code or the JAX code. Same thing, this is for scalar function, and this is instead if you have a model, which means you have the usual neural network stuff. You have a model that's given some input, some loss function, and some data set to iterate on, compute the action, compute the gradient, the action, and everything is automated. And also the creation of the solver is automated. So once you have a function, you have some configuration, like I want to use trust region with these parameters, and the solver is created, then you just do solver.train or something like that, and you can solve the problem. So
Stefano, can I ask a question here on the
yes,
use
please.
of DeepXD? Yes. So if I go to DeepXD and I want to solve the Poisson equation, if I interface with your library, then I can actually run second order, my solver to be second order, right?
Yes, the only thing that, yes, but wait, there is one caveat. So the interface that I have with DeepXD is very, very primitive, because it's just the only one that I needed to do DeepONet. So I never tried to use pins, because pins are very easy to be implemented, right? So I always implement it by myself. So I know that you have some, in DeepXD, there are things that, since you're doing PyTorch, there are things that are, passed around, like, the PDs, the PDs on the collocation points, and it needs someone that knows the thing to spend probably an hour or so to actually refine what I have for DeepXD. But yes, yes, you can do that.
No, I see. Okay, thank you.
Yeah, it's more or less a setup. So the other thing that is something that I still don't have with the DeepXD is that you handle some way the way you iterate on the data set, what for me is more like a Python way of iterating on something. So it's more like it's more Pythonic. So the data set, the data sets that the DeepXD setups, they're not really well exposed to the framework. But if someone is fluent in Python, it won't take much to actually do it. So the cost, clearly though, this library is an overhead, right? How large is the overhead of this library? Because usually when you work in native mode, let's say JAX or Torch, and you have a neural network, your parameters are dictionaries or something like that, and you never linearize the memory in a flat, or let's say flatten or fold the memory to interface with linear algebra, right? Or if you do it, it has a cost, right? And what is this cost? And this is what you can see here. This is for a 3-layer CNN with 5 million parameters. Comparing objective gradient and Gauss-Newtonation with a single batch computation on MNIST dataset. So this is grayscale 20 by 28 images. So in solid lines are this is JAX and Torch using PETCML, and this is JAX and Torch using instead the native mode. So when you want to compute an objective function, you see that you have some overhead because you have to flatten and fold the data back and forth when you want to compute the objective function, right? The point is that this is below this is around the what is that 2 milliseconds or something like that. It's the actual cost, the extra cost that you can see, but the soon that you crank up the batch size, or for larger batch size, this cost is actually negligible. You don't see it anymore. And this is actually doing the Escher the Gauss-Newton Escher matrix better product, and you can see that the cost in JAX is the same as doing the gradient. For PyTorch is a little bit higher because this is also dependent on the specific backend implementation of the autograd. So in JAX is much more natural to do it. With PyTorch is a little bit convoluted, and you get some extra cost there. So numerical results. First of all, some results for pins. So physically informed neural networks. So we decided to test pins in a framework for which we don't know of a good solver for in FEM or finite differences, which is what is called the infinity Laplacian. So the infinity Laplacian is the symbol is here. So the infinity Laplacian is the action of the Hessian of the scalar function on the gradient. So this is a PDE that has no weak form, which means this is not expressible in divergence form, which means you cannot use it's you have to do tricks to use it in finite elements or other methods that use weak forms. And it is the limit for P that goes to infinity of the P Laplacian. So solvers, even FD solvers, they are quite complicated. And also, if you want to actually solve the infinity Laplacian, you have to crank up P, and because you want to solve for P equal 1, 2, 3, and do some sort of continuation, have to solve to actual P infinity, because otherwise, you will never converge. So here we want to test if physically informed neural networks can, solve this problem to some degrees of accuracy. We were really not interested in the in actually accuracy, but actually to really see if we can get close to the solution, right? And we tested on the model problem of the infinity Laplacian, which is discrete harmonic infinity Laplacian. So you set some boundary values, and you want 0 discrete infinity Laplacian in this side. And there is evidence that the solution is known in terms of viscosity and solutions, and it is there is evidence that by work by Wee and Wojtowicz that says that deep neural networks can approximate viscosity solution of PD. So why not using pins? And actually, you can use pins. So we didn't spend much time on that because always getting the balance of boundary loss, internal loss. It's difficult sometimes, but we tried many different solvers. The only one that worked was with the Gauss-Newton solver, where here you see the convergence history. BFGS, Adam, we tried many times with many. We did some hyperparameter tuning to see if we can really actually use those methods to solve the problem, and the solution was we couldn't. We really couldn't really pass the first stagnation of the residual. And the solution is this, Jamaican flag style image, and this is, and compared to the exact solution, we get some sort of, we really didn't want to actually improve this accuracy here, but just to see if the solver is robust enough compute this kind of problem, and the answer is yes. Then we said, okay, why we don't do some other thing, which is we try to do to use Gauss-Newton to improve results coming from molecular dynamics simulations. So why people want to use machine learning techniques in molecular dynamics is because potentials that are needed to actually do the simulations in molecular dynamics are quite expensive to be evaluated. Okay, because usually it's an n-body problem. So you want to use machine learning to create a surrogate of these potentials that are databases in coming from DFT theory, and so that you have a quick way to sample, a cheap, let's say, way to sample the potential and speed up the overall molecular dynamics simulation. So here, what we try to do is, okay, we took, so none of us is skilled in molecular dynamics, so these results are just for us to have an idea of, can we do something with this kind of methods also in here? So we took some IPython notebook from JAX that does molecular dynamics, that also provides converged solutions, and this is let's say this point here, and these are the scatter plot of the training data. Sorry, the training data and the test data, so the unseen data. So these are scatter plots. So this has to be aligned with the. So this has to be on the XY line. So if they are to, so the scatterer, they are the worst approximation property. So we started from this kind of configuration where potentials and forces have been already trained, and run Gauss-Newton for 1,000 iterations. So this is not really your usual Newton method, because you're basically going down 1 order of magnitude in the loss, and you take 1,000 of iterations. So it's quite expensive, but can you improve the approximation properties of the learned potential? Visually, yes. Okay, if this translates to improve solutions in the MD simulation, I'm not the one supposed to judge this thing, but what I was interested in is, can we use this kind? So this is a graph neural network. It's complicated. It's 200,000 parameters or something like that. So yes, you can do this. So to finish, the operator learning, I will go fast because I guess the last 5 minutes or so. But all these, the last results for operator learning are all in this paper that they just appeared in the ACM. In the ACM journal, and so if you are interested, you can see all the results that I have here and more with more details. So the idea is we want to use second order methods or BFGS and use them on the same data sets and same configuration that has been used, that other solvers like Adam or whatever has been chosen by the authors of different papers and work, to validate the results and see if you can actually improve the approximation properties, which means improve the generalization error. So using the same data set, same solvers, everything. And to do that, we also decide to fix all the hyperparameters of our model. So trust region, we are not changing the hyperparameters of trust region for FNO, DeepONet, or green learning. They're all the same. Same for BFGS, same for Newton. Okay, because we really want, the point we want to make is, we really don't need much of hyperparameter tuning to improve approximation properties, and those are the details. So the first results are for FNO. I guess more everyone on the call knows what FNO does, and the first thing that we tried to reproduce was the Burgers equations test case in the configuration configuration proposed in the paper. I guess is your fair comparison that you use a coarse representation of the data that still has very good approximation properties also for FNO. So the idea is, so here the results now for operator learning are always given in this kind of plot. So on the left column, you have loss function. On the right column, you have test matrix. On the x-axis, you have epochs. And this is the value of the loss function or the test metric. Okay, this is in terms of iteration numbers, or this is in terms of oracle calls. Okay, so this is agnostic measure of the computational cost. And here on the legend, there is always the minimum value attained by the solver. Each of the solver tested for the loss function in this case, and for the test metric here. Okay, ref is always the solver that has been used in the literature to validate the model, and we always get very, very close in agreement with what has been published in the literature. So for example, for FNO here, we get 1.4, 10 to negative 3, and this was Adam with some batch. So we actually match the exact configuration of the solver here. And here you can see that with the same data set, everything, you can get, or you can get almost 2 orders of magnitude speed up in terms of, approximation errors. So if this is important for the application, it's not my core, because
can you go over the legend one by one?
So yes, ref in this case, ref is always the reference solver used. So in this case, I guess it was Adam. Okay, this is explained in the paper, but this is always the solver that has been used in the paper of FNO. Actually, this was your paper to validate, to compare FNO with DeepNet. I
just want to know what the rest is.
LBFGS is BFGS.
Sure.
LS is inexact Newton.
Okay.
LSGN is inexact Newton with Gauss-Newtonation. Trust region is trust region, and TR is trust region with Gauss-Newtonation. Okay, so this is trust region with full Hessian. This is inexact Newton with full Hessian. So this is, the Hessian is indefinite here. Okay, so these are the different.
LSGN is what? The blue is what?
LSGN is inexact Newton with Gauss-Newton approximation of the Hessian.
What does mean inexact Newton? That means formally not second order.
No, inexact Newton is this one. Inexact Newton is, sorry. You actually don't solve exactly the step equation, right? You always do the usual thing. You solve it up to a tolerance, right? And usually this tolerance is dynamical. This is why I call it the inexact Newton.
Okay.
Because because it's always you don't want to oversolve here, right? And even not oversolving, you see how much time you spend in the initial plateau phase. And these are log scale. So this is these are already hundreds of iterations. Okay, so this is not the usual Newton method. Okay, but it works. So at some point it enters the.
Basically, you're showing that you can get the same error as LBFGS, but
yes,
2 magnitude faster in terms of iteration.
In terms of iteration, yes. But what I care about is oracle. Oracle calls, yes. Oracle calls, yes. Here is the LBFGS. More or less with the same cost, you get what half. You improve an half of still an half of yes. That's I really don't know if half is decisive or not for the application, right? The whole point is, there is something on there in the data that we are not really exploiting to improve approximation property, and the
problem is with the overhead the problem with the overhead that you show, the overhead for the Hessian and the gradient, right? That you show us.
Yes, the overhead to compute them is it's more or less is the cost. The Hessian is the cost of the gradient. Is that so yes, here you get 100 times more oracle calls, but this I presume is the result of a huge sweep of a hyperparameter sweep to get the best possible generalization error for Adam in this kind of and this is a single run. Okay, so if I do 100 runs of Adam, I will get here. You see the point of computing cost.
Yeah.
So second thing is, okay, can we do with more complicated problems? Yes, this is the 2D Navier-Stokes equation where you learn the using the first 10 seconds, you learn the next 30 seconds of the simulation. Results are very, very similar. And actually here the costs are, they are more closer. Yes, you spend more, but you spend it once, and you get more or less, half here. Okay, half. 2x speed up in terms of generalization error here. And as you can see here, there is no LS or TR because, in this case, the full Hessian matrix vector product, went out of memory. So because Newton, you can do that. Then, DeepONet. For DeepONet, the first thing that I have is, learning the map from the reaction, the forcing term to the final solution of the reaction diffusion equation. This is one of the data, and this is very, very similar things. And I always get numbers that are very close to the one reported in literature using the same solvers. And here, and even here, you get more or less one order of magnitude improvement. And in this case for DeepONet, in general, I found DeepONet easier to be trained than FNO. And actually, FNO is a little bit more expensive to evaluate. And but in general, also the problem is, at least this one, it was easier to be trained. Then I also have DeepONet POD, so where you learn the map from the initial condition to the space-time domain solution of the advection equation. So these are case 2 and case 3 in your paper. This is case 1 and case 2 for me, but these are case 2 and case 3 for your paper. Very similar things. So you get here is 4 times smaller and almost one order of magnitude smaller if you use trust region with full Hessian. Okay, and again the costs are comparable or better using second order methods, but here no hyperparameter tuning because it's the same parameters for all I could have improved this by playing with hyperparameters of Gauss-Newton or trust region or BFGS or trust region, but I didn't want to because that was not the point. The point is, so as you see, even BFGS is always very good. If you ask me, BFGS is always very good in computing approximation, the approximation of the neural network. And so case 2, very similar. This was very, very easy. So DeepONet POD and DeepONet RD, you can run it on the software that is public. The FNO no, because I didn't have time to port the IQ, JAX IQ backend. But and this is also the last thing that I want to show is green learning. So so here the construction is quite similar to DeepONet, but just is phrased in the context of the green learning of the green functions. So the idea is that you really want to learn the green function behind a linear operator. So in the case that I choose is the case that we have been used. So this is the Nature paper of Boulay and co-workers, and where they claim that green learning is data efficient, and I choose probably one of the most difficult data points to try to see if we can improve approximation properties there. And the answer is also for green learning, yes. And data is here, so you can see even here you will get almost one order of magnitude improvement. So for example, here inexact Newton with line search failed to converge. So this is the only case that we found that line search failed, and you can see that this is when Newton fails in the in the early stage of, not really early stage in terms of epochs, but early stage in terms of residual reduction. But this was the only case that where the line search was unable to find a good descent in that direction. But even here, one order of magnitude improvement, and even here, here this is the same computational cost here. So we are almost already, we have already squeezed all the approximation properties that we could with the same computational cost. If we'll go to the conclusion, then I can take questions if you want. So I think I hope I convinced you that using conventional second order methods can be beneficial when you want to train neural networks and in the scientific machine learning context. And in all the results that I have, trust region with Gauss-Newton is the most robust in terms of in computational costs. So this is discussed a little bit better in the paper, not here, because I didn't have time. Clearly, this is not the end of the story, because for once, we choose different contexts, different networks, different data sets, but there can always be something that breaks the solver. And then there is still work to do. For example, how do you precondition the tangent problem? And how do you precondition the nonlinear problem? How and if these results extend to classification problems? And so those are things that we are still working on, and we hope to publish soon, and for which I'm always open to collaborate or give information. Okay, I'm done.
Great, thank you so much, Stefano, for this nice presentation. I've done a lot of work and explore many things. Do we have any questions from the audience?
Hey, Stefano, this is Raj. I'm from Brown. I just had a question. The example you showed for FNO and DeepNet, this is with batches, right? The training is with batches.
For FNO, yes. Okay, so this I went through quick, but I always reproduce the same. So basically, I took the code that people publish with their paper and use the same optimization solver that they use. So being Adam or SGD or whatever, with the same batch configuration, same data set, everything. Okay.
Yes.
So for example, FNO for these two cases, for the Navier-Stokes and the Burgers, yes, this is batch, but this is only the reference solver is batch. All the other solvers are always, full data set. I mean, so I use the same mini batch size, but I always iterate on the data set. So this is a full gradient, full Hessian. Okay, is it clear?
Yes. Okay.
It's
so
not, but for DeepNet, at least there is the examples that I've shown. They were not used in mini batch configuration to actually present the results. At least the codes that are public, that can be run to reproduce this kind of results for DeepNet, they were not using mini batching. They were just using full data set batching to do the optimization. And this is what you can see it here. Actually, this is quite clear, right? That it's using full batch stuff, because at some point this is actually going wild. But yes, in this case, it's not mini batch, because it was not used it was not using any mini batch in the original paper.
okay.
Same for green learning.
Okay. So did you observe any like warm-up issue, because you still have a ill-conditioned Hessian matrix, right? So do you have to start optimization with first order and then move to the LBFJ?
No, because again, so as this was, so getting this kind of solvers to work can be tricky and requires, and required a lot of, years by a lot of people in the past. So yeah, we are just standing on the shoulders of the giants for, in this case. So there are safeguards in place already. So for example, line search is very, very important for Newton. If you mess up the line search, if you don't have a line search, Newton will never converge. If you mess up the safeguarding the safeguarding tolerance, Newton will never converge, because it will try to oversolve at the beginning and never, something that may happen here, for example, try to oversolve at the beginning and never converge. So using the whole point of using a library that has been written by others by 30 years and validated is because all these kind of things, they are in place and you don't see them, right? For example, for trust region, one thing that was important for us that is now part of PETSI2 is that at the beginning, so there is a concept of transition which is called critical point, Cauchy point, and the Cauchy point says, is the maximum reduction that you can have in the direction of the gradient, and it's called the Cauchy point. And if you use, there is a couple of books that discuss this. If you use when the Cauchy point is outside of the trust region, or actually it's on the trust region because you compute it by definition on the trust region, you always, you have to pick the Cauchy point instead of solving the actual problem. And this is what happens, for example, here in trust region. In all the cases here, you never basically solve the linear problem here. You always take the Cauchy points, and then automatically the solver start to use start to solve the tangent problem. But this happens later, and so yes, I never had to do this kind of warming up because those are the oversolving, the oversolving tweaks that are in place that helps you there. But yes, I understand that you may have issues, but all these kind of solvers, they start from the same random configuration.
Yeah, I just have a last question on your slide 29. So if you can make slide 29. Yeah, here. So this, you see that at second batch, the point you have just kink on only that batch size. Is it kind of caching effect or something else?
I don't know. I really don't know. So this is 10 runs. So out of 10 runs, I remove the outliers, so the minimum and the maximum time, and then I take the mean of the timings. Okay. So for JAX, for example, I know how to block the operation to say actually return only if the operation is finished. I don't know how to do it with PyTorch, for example, and so this can be actually very well be that the cost, the way JAX maps the operation of with this specific batch size, that doesn't really map very well on the GPU architecture. But I don't know. I really don't. These kind of kinks are artifacts. What I really care is the fact that the overhead is in the order of the millisecond.
Yeah.
Of the millisecond, and it's a significant overhead. This is twice as costly. Okay, if you care about the factor, this is twice as costly, but in the milliseconds regime, and this is a very cheap objective function. But as soon as you go on the other part of the spectrum, where if you fill up the batch size, the overhead is minimal. But yeah, I don't know what I really didn't investigate this.
Yeah, I have an immediate problem with one of the examples I'm doing, so I think I will check out your library and maybe I can contact you with some.
Yes, please. Please.
Yeah. Okay. Thanks.
So Raj is Raj, turn on your camera. Raj is associate professor here at Brown, working in a group.
Yes.
Good. Yeah, that was as I said, the reason I wanted to I was very glad to give this talk is to really you don't want to do this work and have other people that can benefit of this thing, right? To see if they can improve their results.
I have one last question. I have a problem with turbulence where I'm using 1024 GPU and pin kind of gets stagnant at 10 to the power minus 3. So I mean, I use 1024 GPUs, A40 for that. So I was just thinking to use this optimizer to proceed from there and see that, since you mentioned that it is a multi-GPU in the data parallel sense, right?
Yes, yeah. The only thing that I have so far is what is called the data parallel approach. Yes. Model parallel, I'm not that far from it. It's it's just to have just to know how this
Raj
kind
is doing the data parallel.
I'm doing two actually, CPIN and the data parallel both. I'm just measuring that which one is more accurate. So in the CPIN, I have a point-to-point communication, unlike data parallel where you have collective communication. So I have both examples set up. So I just have a trained model at that point, and I just want to restart with your optimizer, see that how does it scale on such a large GPUs, and if I get any benefit out of it.
Yeah, so you do data parallel, which means that the batch size is actually the sum of the batches on the GPU.
Yes.
Right?
So there are local batch size, there are global batch size, right?
Yes.
So the global batch size is almost close to 500,000.
Okay, nice.
And within the GPU, I have almost 100,000 like batch size. I can play with that, but I'm not
Yes.
sure that how
So
much.
yes,
So how much?
multi-GPU, yes, multi-GPU
Yeah.
works and uses Nickel. You
Yes.
can also use, plain MPI if you want, but
Yeah.
you can also use Nickel directly. You don't see it, but it uses Nickel. Yes.
Okay. Yeah, I might ask question on your GitHub and Git issues.
Yeah,
so-
please.
Yeah, sure. Thank you, Stefano. Very interesting.
You're
talk.
welcome.
Stefano, we had a speaker here from Spain. His first name is Jorge. I forgot his last name. Maybe Elham can help me. And he presented optimum solvers with BFGS, not LBFGS, but BFGS.
Full BFGS.
Yeah, full BFGS, and for similar problems, pins and he was getting really good accuracy.
Yes.
He was also tuning the loss function, I remember. But Elham, do you remember the paper? Maybe you can,
I
or the
can share
author?
the paper in the chat. Yeah.
So BFGS, in my experience, is a great solver. If someone always give me an optimization problem, the first thing that I try is always BFGS, because when it works, it's unbeatable. It's very fast, and is the to-go solver in unconstrained minimization, right? So, and in my experience with training problems, BFGS always gives very good results, even in the limited memory,
No, the LBFGS, yes, it was obvious what you did, but I'm talking about accuracies. You show you beat LBFGS by a little bit, let's say less than an order of magnitude, but BFGS, you were getting really, really good results down to machine accuracy.
Down to machine accuracy, really? Okay, that is, yeah. I can if you send me the paper, I can see if I can reproduce.
I don't know if
Elham
found. Elham, did you find it? It disappeared. She will probably find it.
Yes.
Anyway,
Okay, it's you.
I think that Elham put a.
Yes. Could
yes,
you see
sorry.
that?
Yeah, Jorge Urban. Yeah, Urban.
Urban, yes. Okay. Yes, I got it.
So I don't know if he's not, but he's an optimization guy, and he has a kind of two different ways of pursuing this, but one is basically BFGS. That was the
yes. Thank you, and I will read it.
And relatively small, that's like he says, typically very small compact networks like this, and it's kind of along the lines that you are pursuing, namely focus on optimization. And it would be nice actually to see how one can combine the two, because he's doing also some tricks and compare the two. For us, we have this theory. Juan, who is the host, is one of the co-authors of the theory on learning pins, and turns out that we have discovered three phases using information bottleneck theory, where you go from bringing down the loss to zero, close to zero, then that's fitting the data. Then you go through the learning process, the generalization, and there's a diffusion and then total diffusion. And we correlate that to Adam optimizer. So if you plot the correspondingly how Adam works, then you sort of follow that. In other words, the stochasticity helps us, and so it would be nice to see how this learning theory changes for second order solver. So
yeah, that was that was one of the things that we were looking at the beginning, right? Because when you started with a new problem, you really don't know what you have to look at. And so, for example, I can tell you, I remember still how this pattern was forming. So you couldn't see, with Newton, you couldn't see anything. okay, for quite a long time. Then at some point, you know, those bubbles started to populate from one corner and move to the entire domain.
Yeah.
And then, you know, there was a second thing where,
Right.
you know,
That's why I actually thought about it, because
when the boundaries were actually refined.
Yeah. Our theory introduced this RBAs, the residual based tension weights, which promotes this because it spreads the residual to uniformize the residuals much faster than if you're not doing anything. So that's one. But then we see also the correlation with Adam. So I think one put the paper on the chat, which is another archive paper. If you can take a look at it, and you will see some plots that have Adam and then together with the.
If you can go to the figure 10, like if you open the PDF and you go to figure 10.
Because that's something that nobody has explored. We were, I think, the first to kind of associate learning with, and we track the signal to noise ratio, actually, one quantity, but
yeah, here.
Yeah, right here.
If you, in this one, the green line is this kind of SNR from Adam, which is essentially just in Adam you have like this momentum, right? Like you have momentum and so on. That's how you somehow tweak the learning rate. In Adam, that's how it works. So it's kind of like you play a little bit with this statistics, and you can extract some signal and some perturbation from that signal, and that's what you see in green. And when you see in red is like the SNR, and what in the SNR, where the measuring is like how, as George was saying, like how sparse the results, how uniform the results are. So that's this SNR.
The residuals, uniformize the residuals.
The result, how uniformize the residuals, the errors, the pointwise errors of your model are. And then,
but at the high level, because we have to go to the other talk, at the high level, there's a connection between the learning and the theory of learning for pins and other neural networks and the optimizer you're using, because that induces stochasticity, which is very important for the generalization. So these vertical lines show you when you actually start learning. So the first part, you sort of bring the loss function down to small values, but you haven't learned anything, just fit the data.
Yes.
The real generalization
is
during these two other phases, which we call diffusion and total diffusion. So
which align quite well, yes.
Yeah. So
which align quite well with what we were looking at. Yes, no, those are all things that are very interesting to look at. Yes.
So that's a good thing. We can together look at it. But thank you very much for taking the time today. I know.
Thank you for to give me this opportunity.
In Italy, and lots of things happening at night in Italy. So thanks for taking the time.
No, it's beer time now.
Okay.
Thank you so much, Stefano.
Bye. Thank you.
We have a second speaker. Haoyang, are you in the call? Yes, I see you there.
Yeah. Let me share my screen.
Yeah. Okay.
Oh. Can you see my screen? Can you hear me?
Yes, we can see your screen. Thank you so much, Haoyang, for your time. As mentioned a few minutes ago, we have a second speaker today. His name is Haoyang Zheng. He's a PhD candidate in the School of Mechanical Engineering at Purdue University. Previously, he was a Gibbons Associate at Argonne National Lab in 2023. His research topics include Markov chain Monte Carlo, uncertainty quantification, data-driven modeling, physics-informed neural networks, operator learning, AI for science, etc. His research focuses on the use of computational and analytical tools for differential equations to tackle complex challenges in machine learning. He has published work in renowned journals and conferences, including NPJ Digital Medicine, Journal of Computational Physics, International Conference of Machine Learning, International Conference of Artificial Intelligence and Statistics, and others. Haoyang, with this small introduction, you can start whenever you're ready.
Great. Thanks for the kind introduction, and thanks very much for the invitation from Professor Karniak-Dakis. It is my pleasure to give a talk at Crunch Seminar. And good afternoon, everyone. This is Haoyang Zheng, a PhD student at the School of Mechanical Engineering, Purdue University. So today's for my talk is on sampling tests with Langevin Dynamics. I would like to share of our recent works about how to use Langevin Dynamics in different sampling tests. So this talk mainly focuses on these two works. First is on how Langevin Dynamics on Langevin Monte Carlo can be used in reinforcement learning tests, which we also call it Thompson sampling. And this work was now shown in AI Stats, which is a statistical machine learning conference. The second work focuses more on traditional sampling tests. We use a well-known technique in Bayesian inference called parallel sampling or replica exchange. Our motivation is to improve its sample efficiency by a careful design of its sampling region. And this work was recently accepted by International Conference on Machine Learning. And I also want to thank for all my collaborators in these two works, which include Wei from Morgan Stanley, Henrong, who is now at UC Irvine, Shi from Florida State University, Chris and Professor Guanglin, both from Purdue University. And Henrong is also here today, and if you have any question regarding our work, feel free to stop me. So I would like to separate my today's talk into 4 parts. For the first part, I will introduce a concept of Brownian motion, how we summarize such physical motion into some math and statistical tools in stochastic differential equations, and then come up with Langevin Dynamics and Langevin Monte Carlo. And nowadays, Langevin Monte Carlo can also be used in training deep neural networks, and we'll explain how does it work. And then we will use the power of Langevin Monte Carlo to parameterize the distributions in 2 different tests called Thompson sampling and constrained exploration. So I will start with the problem definition, the motivation behind our work, the design algorithm, and the results from both theoretical analysis and experimental validations. And lastly, I would like to briefly mention our work in scientific machine learning if we have some extra time, which includes data-driven model discovery in Alzheimer's disease. And we also worked on pins, which we combine homotopy continuation and pins to address some inverse problem. So let's move on to the first part. So machine learning and dynamic systems are concepts from different fields of science and engineering. There's a lot of intersection between these two, and some machine learning algorithms are actually inspired from the idea of dynamic systems. Some may perform well in machine learning tests, and we want to make them explainable to provide some intuition behind why it works well, like the residual neural network. Some algorithms like Langevin Monte Carlo diffusion models get ideas from dynamic systems, and the scientists develop them to become a powerful tools in machine learning. So this is, from my perspective, very important because now your model is no longer a black box. You can explain why it works well to some extent. And also such algorithm like Langevin Monte Carlo actually provide a confidence interval to your results, which means your results is no longer a point estimation. And this is very meaningful because in many engineering fields, people not only want to know the results, they actually care about how confident you are in the results. Okay, so let's first go back to the 19th century and see how such fantastic algorithms were first observed from the real world, construct them to mathematical tools, and finally use them in machine learning. So the first discovery of Brownian motion can trace back to 1827. Botanist Robert Brown made the first observation that pollen seeds taken from flowers suspended in water. So from the microscope, he found that the tiny grains suspended in water appeared to make random zigzag motions. And this motion never appeared to slow or stop. But at that time, he could not explain why it occurred. A better understanding of Brownian motion came later when Albert Einstein gave the first mathematical model in 1905. He explained that if tiny but visible particles were suspended in a liquid, the invisible atoms in the liquid would bombard the suspended particles and cause them to jiggle. And this irregular random motion of the particles could be directly observed on the microscope. So this is a 2D simulation of what you can see from a microscope of water molecules. They behave irregular, but this motion will never stop or even slow, and you cannot observe any pattern or predict its future behavior. And it is because of the collision of water molecular is random, which makes the trajectory to be irregular. And later, Norbert Wiener summarized such rule and provided a no understanding of Brownian motion by introducing the Wiener process. He provided a rigorous mathematical foundation for it, that paths generated by Brownian motion were governed by probability laws. And now we can model the stochastic process mathematically and apply it in a wide range of applications like physics, finance, and engineering fields. Later, Kiyoshi Ito extends the study of Brownian motion with Ito calculus, which extends classical calculus to stochastic process. His work, like Ito's lemma and the stochastic differential equations, become fundamental tools in the analysis of Brownian motion. So nowadays, after long years of development, this simple physical phenomenon was applied in machine learning to model the absurdity and randomness in the real world. So Langevin dynamics is developed from Brownian motion and can be described by stochastic differential equation. It generally includes two parts, the gradient flow and Brownian motion. So if you first ignore the second part, it is just what we use in the optimization algorithm like gradient descent or stochastic gradient descent. If you further consider the second part, it becomes more interesting because when the time t goes to infinity, its empirical distribution will converge to the target distribution pi. That means even if you do not have access to the function f, you can still approximate it with gradient information. And of course, within limited time, there's a distance between the posterior given by the SDEs and the target. And our goal is that if we want to make the distance between the SDEs close enough to the target distribution, how much time or how many samples we should pay for them. And in SDE, this is defining a continuous time. And so when you implement this algorithm, you need a discretization scheme to let it work in the computer. So what we commonly use strategy is called the Euler-Mariana discretization. That means we first do gradient descent to get the mean and sample from a normal distribution where the variance is from the Brownian motion term. So beyond the naive Langevin dynamics, there are a lot of variants to improve its convergence rate. And here we provide, we would like to introduce 3 variants, which will also be applied in our work later. So the first one is called underdamped Langevin dynamics, which incorporates the momentum term in the stochastic differential equations. And because of that, it can converge much faster. The second one is called replica exchange Langevin dynamics, which we consider 2 SDEs or 2 chains with different temperatures, where the low temperature chain updates slow and can better characterize local modes. So it focuses on exploitation. The high temperature chain updates abruptly and can easily escape local minimum. So it focuses on exploration. We can also design a scheme to swap these 2 chains regularly. So then the low temperature chain can escape local modes to characterize all the modes efficiently. The last one is called cyclical Langevin Monte Carlo. So for the first 2 algorithms, we may consider constant step sizes to implement them. And here we use a cyclical step size. So if the step size is small, it focuses on exploitation, and a larger step size focuses on exploration. And we also provide a video here to show why these variants are very efficient, and later we will introduce in more detail when we use them. So here's a task to characterize a target distribution with 25 local modes. So you can see the orange circles here are local modes. So there are 5 by 5 equals 25 modes. You have to characterize them and try not focus too much on one mode so that you will not miss other important modes. So you will see the naive Langevin dynamics get trapped in the local modes, and underdamped Langevin improves the results a bit better. But when you see cyclical Langevin Monte Carlo and a replica exchange, they can easily escape local modes much easier and better characterize all the modes because of their design. So we also want Langevin Dynamics to work with some complicated tasks like training deep neural networks. So one of the challenges when we implement gradient Langevin Dynamics, calculating the exact gradient can be very expensive if the data size is very large. So to make the implementation more efficient, we replace the exact gradient with an unbiased estimate of stochastic gradient with mini-batch data. Well, it includes some bias during training. It will finally converge to the target distribution if we consider some strategy like diminishing learning rate during training. So here, we want to share some reasons on why we should consider SGLD in deep learning. The first point is that the loss landscape in deep learning is highly complex and multimodal. This means the posterior distribution does not strongly favor any single solution. So there are a lot of equally valid solutions within the loss landscape. So relying on a single point estimation is often insufficient to accurately reflect the ground truth. Another concern comes from the perspective of reliability and security. So when dealing with large data sets, which are typically trained with optimization like SGD or DAM to produce a single point estimation. So this approach can lead to inaccurate uncertainty estimation and unreliable predictions. So for example, the model may become overconfident when making predictions of certain data and can be easily deceived by adversarial examples. To truly reflect the complex landscape of deep learning models, we need better posterior approximations. So SGLD can provide a more robust approach to characterize the complex loss landscape and more accurate uncertainty representations. The last point is that at each mode in the loss landscape correspond to different representations of the data rather than being simply due to the noise or rescaling. So combining these diverse representations can lead to improved understanding and higher accuracy. Okay, so I will pause here for a while if you have any questions.
Do we have any questions from the audience?
Okay, so if you,
okay,
so if there's no question, then let's move on to see how we use Langevin Dynamics in our application. So we will first introduce Thompson sampling. Okay. So as we mentioned before, Thompson sampling is a Bayesian version of reinforcement learning. So I would like to start with the introduction of a simple reinforcement learning algorithm called multi-arm bandits. So suppose there's a time horizon big N and runs small n from 1 to big N. And we also have k arms. So for each round, the agent select one arm and receive the reward. And according to the reward, we update our strategy to select the next arm. We further define the regrets, which is the sum of the best rewards that we could get minus the sum of rewards that we actually get. Our goal is to find the optimal strategy or find the best arm so that we can maximize the rewards or minimize the regrets. So here's an example in the use of multi-arm bandits. So suppose you visit a new city and there are 3 restaurants, and each time you need to select one restaurant to visit. The question is that you do not know the rating of each restaurant, but every time you visit, you rate the restaurant and you update your strategy for your next visit. Your goal is to find the best restaurants to maximize the average rating. Okay, so that is multi-arm bandits in the frequent setting. So what about it in the Bayesian framework? Now we assume a posterior distribution for each arm, and each time you sample from each arm and compare the sample, and then select one arm, and then you receive the rewards from your selection. According to the reward, you update the posterior distribution and so on. Then your target is due to maximize the rewards or minimize the regrets. So from this figure, so suppose there are 3 posterior distributions characterized by 3 arms. You sample from 3 posteriors, and the dashed line here are the samples you generate. And then you compare them and find the first arm is the largest one. So you select the first arm and receive the reward. And then you update the posterior distribution of the first arm, and the other two arms keeps the same. And you do the same thing, sample, select the arm, receive the reward, update the posterior, and so on. So Thompson sampling algorithms is easy to implement it when you consider conjugate distribution like beta distribution. So for beta distribution, you only need to update alpha and beta here, and then you can easily characterize the posterior. And also for Gaussian distribution, you only need to update the mean and the variance. So the question is that if we do not want to use conjugate distribution, and can we parameterize or approximate the posterior distributions? So this is, from my perspective, a very important question in Thompson sampling, because nowadays reinforcement learning can do a lot of fantastic things like playing chess games, play video games, and ChatGPT also consider reinforcement learning. So can we do similar things in Thompson sampling? So, well, this is why we consider Langevin Dynamics to approximate the posterior and used in Thompson sampling. So the Langevin Dynamics was first applied in multi-arm bandits in this work, which to my knowledge is the very first work to consider Langevin Monte Carlo in Thompson sampling. And later it extends to contextual bandit and also Q-learning. And this is good. And the next question is that how can we improve the performance of Thompson sampling? Well, it is because I realized that the existing works focus more on the use of naive Langevin dynamics or the overdamped Langevin dynamics. And in MCMC community, it is well known that higher order methods like underdamped Langevin dynamics should converge faster than the naive one. So can we see similar improvements when we implement higher order methods in Thompson sampling? And this is our motivation to provide a detailed study on how high order methods can improve the performance of Thompson sampling. And this is why we first validate the performance of Thompson sampling with underdamped Langevin and compare it with overdamped Langevin. So we test them in different dimensions and different number of samples we use. And here, the smaller regrets, the better the performance. So here, square root of D and the D samples here just refer to different learning rates when you're training a neural network. So square root of D samples here can refer to use large learning rate, and D samples refer to small learning rates. So you can see when you use large learning rates in Thompson sampling, you will see overdamped Langevin will fail to and yield linear regrets, which is bad. But our method can still get sublinear regrets like this one. And if you use smaller learning rates to guarantee overdamped Langevin to get sublinear regrets, you will see when we consider underdamped Langevin, the regrets are much more smaller than the overdamped one. That means same as what we know in MCMC with high order methods, Thompson sampling also performs better, and which is good. And the next question is that, can we theoretically prove that if we improve the computational complexity in Thompson sampling, will the performance gets better? So before the analysis, I would like to provide more intuitions on why underdamped Langevin dynamics can improve the convergence rate. So there are two equations here. And if you first look at the second one, Vt is the velocity and xt is the position. So this equation just means the current position is just integrating the velocity over time. And if you look at the first equation, the first term here is called friction term. So that means as time goes on, you are losing the memory of the velocity or the gradient information. The second term here called acceleration term, and it gets the idea from Newton's second law. So minus the potential energy, you're actually adding external force to the particle and accelerate it. The last term is just Brownian motion term. And then to implement it in the computer, we're just integrating the discrete underdamped Langevin dynamics up to its step size h. And our analysis use the same assumption in ICML 2020. We assume the log likelihood and reward to be convex and smooth. And when you consider Thompson sampling approximated by Langevin Monte Carlo, you have to be very careful about the prior selection and the discretization scheme because improper selection will make it fail and incur linear regrets, just like what we saw in this figure. So for the prior, we adopt a strategy commonly used in MCMC called warm start. So we upper bound the distance between the prior and the target with a constant b. And for the discretization scheme, there are two commonly used strategies. For the first one is to consider a Metropolis Hastings step to correct the bias. With this correction, there's no need to worry about the discretization error. And the other strategy which we prefer in our work is to consider a diminishing discretization error with a rate of 1/n, where n is the number of times we play the arm. And with this consideration, we can guarantee the algorithm can get some linear regrets. And so because it is a long proof here, we provide a general outline of our proof. So we start to assume for the current round, each arm follows SDEs characterized by the posterior distribution, and we analyze the posterior concentration rates given by these SDEs. And then with this posterior, we analyze the number of steps required to avoid linear regrets. And then we implement Langevin Monte Carlo to approximate the posterior. And finally, with this guarantee, we further analyze the posterior concentration rate approximated by the Langevin Monte Carlo. And finally, with this rate, we applied it in Thompson sampling to derive the regress bounds. So for the first step, given the SDEs showing here, we define a potential function and analyze how it evolves according to the SDEs over time. Then we can get the posterior concentration rate like this one. And here is a discretization scheme we use, which are actually similar to the previous one. We just integrate the discrete underdamped Langevin dynamics up to its step size h. And we also consider the construction of gradient information, different construction of the gradient information, which we consider both the exact gradient and the stochastic gradient. So we actually provide a proof for both exact gradient and stochastic gradient. So if you're interested, you can check our proof. But for approximate Thompson sampling, what we found is that it does not influence the convergence rate too much. So that means it is safe to consider stochastic gradient to speed up the computation. And the key point is here is that we proved that we can use square root of d samples to avoid linear regrets, which is actually a significant improvement compared with previous works to use d samples. So here d is the number of model parameters. So that means, for example, if you consider a neural network with 100 parameters to approximate the posterior, well, previous method may require 100 samples to converge. We only require 10 samples to get similar performance. And with this convergence guarantee, we further analyze the posterior concentration approximated by Langevin Monte Carlo, which is showing here the results. For the last step, with the posterior concentration rates, we finally arrived at the regret bound of approximate Thompson sampling, which is showing here. So our regret bound is at the rate of log n divided by delta a. So n is the number of times you play the arm, and delta a is the distance between the optimal arm and arm A. And to sum up, we propose a novel Thompson sampling algorithm with underdamped Langevin Monte Carlo. Our major contribution is a proof of posterior concentration rates given by the underdamped Langevin Monte Carlo. We further derived the regrets bounds of Thompson sampling algorithm, which is same as a previous method. But for our algorithm, we improved the computational budgets from d samples to square root of d samples. Okay, so I think that's the second part of the Thompson sampling. I will stop here for a while if you have any question.
Yeah, hi, this is George. I have a question on the square root of d. What makes the requirement for you to be only square root of d? What is the element that makes it more economical?
I think the requirement is that we have one extra step, like for overdamped Langevin, you only need one SDE, but for underdamped Langevin, you need to first compute the velocity term, and then you integrate the velocity and get the position. So yeah, there's one extra computational step. Does that answer your question?
Not quite. So you mean the friction? The friction is the one that helps you.
Oh, the friction. Yeah.
That gives you the underdamping.
Yeah, that's right. Yeah.
So then in the error estimate, you should depend on gamma, right? If the regret error bound that you have, you should depend on gamma somehow. Can you show me the bound that you, because you only talked about one term, the log n over delta. Can you go to that?
Oh, it is because yeah, I think for this, because that term is a constant term. So what we care the most about the regret bound is number of times you play the arm and the distance.
So where would the gamma comes here in the constant in front of the big sigma?
That's a good question. I think I'm not quite sure, but I think it might exist in like some terms here, but I'm not quite sure. I need to go back to check my paper. Yeah, but I think the main point is that that's a big and of course we need to have a good selection of the gamma value. So unless you cannot get this convergence rate, but I think yeah, for the regret bound, this is not the main part that we care about. Yeah. So we might ignore some details in that. Yeah. Does that answer your question? Oh.
Yes, sort of. Thank you.
Yeah. Thanks for the question. Yeah. Okay, so let's move on to the next topic: constrained exploration with replica exchange. So here's a problem definition. Suppose we have a target distribution pi, and pi is now no longer a uniformly scaled distribution. It is scaled by two different temperatures, tau1 and tau2. And now you want to design MCMC algorithms to see how expensive it is to make the empirical distribution converge to the target distribution. The commonly used algorithm is replica exchange Langevin Monte Carlo, as we mentioned before. So it includes two chains where the low temp chain can characterize local modes and focus on exploitation. The high temperature chain can easily escape local minimum and focus on exploration. And if we swap these two chains regularly, and the low temp chain can escape local minimum and also characterize all the modes efficiently. With this design, we realized a potential issue in high temp chain. That is, high temp chain can easily overexplore the target distribution, especially the tail distribution. It is because normally we do not know the loss landscape, so it can be hard to quantify the best hyperparameters for high temperature chain. So improper hyperparameters in replica exchange can overexplore the tail, which can lead to bad performance. So let's look at some examples to see why it is harmful. Like in the real world, you get a bunch of observations of a Lorentz system from the sensors. And you want to learn the model parameters, rho, sigma, and beta here. And if you consider replica exchange to infer the joint distribution of these model parameters, there are some regions that you might not be interested in because there are some physical constraints that you have to follow. Violating the physical constraints does not help you to solve the inverse problem, but may fail the training. Another interesting perspective is from training neural networks. So we hope to use high temp chain to explore the loss landscape well, but the training will fail if you set the learning rate and the temperature too high. Just like using an optimizer like SGD or ADAM, if you set the learning rate too large, it does not help training the neural network, but you will find the loss will blow up to infinity. And this, of course, will deteriorate the model training and lead to bad performance. This is not what we want to see when we're using replica exchange, but we still hope replica exchange to explore the loss landscape well. And we also know the values of model parameters in neural networks should not be too large or too small. So we believe that constraining the values of model parameters and use a large initial learning rate help us to better explore the loss landscape of our interest. And based on that, this is the design of reflected replica exchange. So you will see we have some extra terms here. So nu is the inner unit vector on the boundary, which denotes the direction of reflection. And L1 and L2 are independent local times, which denotes the magnitude. And here is a figure to illustrate the reflection. So suppose this is the boundary, and we start with this sample and generate the next sample, which is out of the boundary. Then we need to find the closest point on the boundary, and we compute the number vector and tangent line. Then we mirror the sample back to the boundary along the tangent line. And to implement this is a proposed reflected replica exchange stochastic gradient Langevin dynamics, which is also abbreviated as R2SGLD. So for each iteration, we first generate sample just like replica exchange, but if the samples are out of the boundary, we need to consider a reflection step here to reflect the sample back. And then we have the swapping step, which compares the value of U with a swapping rate tilde S. So if U is smaller than tilde S, that means the high temp chain actually find a better local mode. Then we swap these two chains to let the low temp chain to characterize the new mode. Then we do sampling, swapping, sampling, swapping until it finally outputs all samples generated by low temp chain. And next we do theoretical analysis, and the assumption we use here are related to the boundary and the objective. And assumption one is means the domain is compact and the boundary's curvature is controlled, which ensures a good geometry for the sampling region. And the second assumption is a smooth assumption for the objective function, which ensures the gradient does not change too fast. With this assumption, we first analyze the convergence rate of the reflected replica exchange Langevin diffusion. So we here provide two different metrics in chi-square divergence and two Wasserstein distance, and both of them show it enjoys an exponential decay over time. And importantly, we find that the convergence rate is related to the domain diameter. That means if we constrain the region of our interest to be smaller, we can get a faster convergence rate. And then we further analyze this discretization error given by the R2SGLD algorithm, which is related to the learning rate, the noise in the stochastic gradient, and the noise in the stochastic swapping rate. We also did a lot of experiments to validate the proposed algorithm. Like this one, we use the algorithm to simulate a 2D multimodal distribution with a flower boundary. And we also compared with Langevin Monte Carlo and the cyclical Langevin Monte Carlo. We calculate the KO divergence with this to compare which one performs the best. And the smaller the value, the better the performance. You will see the proposed algorithm consistently performs the best. We show more results here, like the left one, we tested with different boundaries like heart shape, octagon, and cross shape. So you will see R2SGLD consistently performs the best. We also compare it with Langevin Monte Carlo without the reflection step, which are showing the dashed lines here. And obviously, you will see the reflection step is very important to a better performance. We further test that the domain diameter really affects the convergence rate. So you will find from this figure that it is true for a smaller domain diameter, it makes convergence rate to be faster to some extent.
So Haoyang, the reflection here helps with the boundaries, right? That's why you have this.
Yeah,
the reflection helps with the boundaries, with sampling at the boundaries.
Yeah. So the blue one is a boundary. Yeah. And if it is out of the boundary, and you will reflect it back.
Yeah.
Does that make sense?
Sure.
Yeah, thank you. Okay, so then we test it in large-scale deep learning tests, like to use residual neural network to do image classification, and we record the performance with different metrics here. So you will see with the reflection, it does improve the performance to some extent. And to sum up, we consider reflection step in the replica exchange and the proposed R2SGOD algorithm, and we provide theoretical guarantee that a smaller region contributes to a faster convergence rate. And we also provide detailed experiments to validate its performance. And that is all I want to share on about our work with constrained exploration. And any question? Okay. So I think I will briefly share some works about our work in scientific machine learning. Okay, so this work is about to identify the disease progression of Alzheimer's disease using a method based on sparse identification of nonlinear dynamics, which we also call it a SINDI. So we developed a causal model in the use of ODEs to understand the dynamics of related biomarkers. So we first learned a population model to discover the general progression of Alzheimer's disease across all patients. And based on the population model, we examined how biomarkers interact to produce diverse clinical and biological phenotypes and identify the key pathophysiology pathways, which affects disease progression the most. And these pathways have led to better treatment strategies in the personalized modeling. It allowed for tailored patient care and optimized treatment planning. And this work was published in Nature Digital Medicine. And the next work is to use pins to solve the inverse problem. But the main charge here is that the measurements are from multiple solutions or sensors, and the measurements are mixed and unlabeled. So before we solve the inverse problems, we have to first classify the measurements, unless you will get a wrong solution. And to address that, we get the idea from homotopy continuation method, which we start with a simpler and related problems with known solutions, check the original problem to the deformed one, and finally identify parameters in the PDEs. So with this idea to adjusting the weights of data loss and the PDE loss in the objective function, we can classify measurements from different solutions and identify the parameters correctly. This work was published in the Journal of Computational Physics. Okay, so I think that's all I want to share today. Thanks for joining the talk, and feel free to let me know if you have any questions or comments.
Thank you so much for your talk, Haoyang.
Thank you.
Do we have any questions from the audience?
Let me ask some questions, and then maybe other people can. So on the can you show us in the pin case?
Oh yeah, sure.
So this is a case where you have multiple solutions. You solve the inverse problems.
Yeah.
And what do you use to? Can you elaborate a little bit on because we have a Zheng who is on the call, has a similar problem for cardiovascular modeling, and it has many parameters. So trying to make it. Can you say a little more? What do you use here? The replica? What do you use? The underdamped Langevin? I didn't understand the connection because you didn't.
Oh, sorry. Oh, I think this is a different topic. So we just use a DEM to optimize this. So yeah, this is another topic. Yeah.
Okay.
Sorry.
So the idea here is that you trying to solve an ill-posed problem with multiple solutions, and let's say the gray Scott patterns that you have there, and you try. How many parameters did you try to estimate here?
You mean the parameter in the PDE?
Yeah. How many parameters? The inverse problem was
Oh,
to,
like we first do some simple simulation, so we just use we just estimate one. So for this grayscale simulation, I think there are 4 parameters we have to approximate. Yeah.
4 parameters. And how do you do that? You do it one at a time.
Sorry, I didn't catch up. I think
So
we
it's not
just
clear
use,
what you're doing. I mean, you describe it at such a high level that unless we read the paper,
oh yeah. Oh,
can
sorry.
you say a little more? We know pins. You don't have to explain pins. Just but
Yeah.
what is the new thing that you're doing here?
So the question, so the problem is that, like, for example, you have these 2 solutions, and when you get the data from the sensor, you select this one, you randomly sample from this one and randomly sample from this one, and the observations you got are mixed, and you do not know which samples you are from. So it is a combined observation, so it may make the inverse problem to be more complicated, and you cannot get the exact answer.
So
Does
you're trying to predict not a single solution, but many solutions. For example, his U1 will be one solution, UM will be another solution. That
Yeah.
like
It is mixed, so you have to first classify these solutions, unless you cannot solve them, right?
okay.
Because
if you don't know, if you say that you don't know which data comes from which point, so then in that case, how do you do the classification?
We just our mainly strategy is like in the homotopy continuation method, like you start with an initial solution and trace that and deform the solution, and finally get the final solution. So I think the general idea is that we have a naive PD solver, and it can the PD parameters in the solver might run, but it help to solve the inverse problem to some extent. And when we adjusting the weights of the PD loss and data loss, it can finally classify all the classify all the observations, and finally get the correct PDE parameters.
Okay.
Mm-hmm.
But when you compute, for example, you say you have an inverse problem, then you have a data loss, right? I think that's what you're showing in the second the second orange purple box.
Yeah, we have
that would be it.
Yeah, I think data loss to some extent can like help you to.
Yeah. Okay. And what is this lambda that you have there? You have a lambda.
Lambda.
Have a lambda multiplying your theta, right?
I think lambda is it's just to adjusting the weights for the PDE loss and data loss. Yeah, it's like a hyperparameter. Yeah.
Okay.
Yeah. So our general idea is like to if we can adjust the lambda value in a very good way, so we can classify these observations from different solutions and finally solve the inverse problems.
Okay.
Yeah. Thanks for the question.
Logan, do you have a question?
Yes, I have a few. So this is one more presentation. I really enjoy listening to talk. And regarding, I think my questions are basically follow-up questions from George. So I've read the original home pin paper. George sent me that paper, I think 1 year ago. So I'm pretty clear of that paper that to obtain multiple solutions from one PDE, we need to solve pins like sequentially. So obtain one solution like the step 1 and to step 2 based on the solution we obtain from step 1, we obtain another one, and we keep going, right? So that's the idea of the original home pin paper. But for this slide, the paper you show on this slide, I'm pretty confused about the concept. So the yield-postness of the inverse problem comes from the multiple solution of the PD instead of the sensitivity of the parameter. So is that correct?
Can you say that again? The problem. Sorry, I didn't.
Yeah. So
follow up.
like, what is the source of the opposedness of the inverse problem?
The source.
Is it from the parameter or the solution multiplicity?
Oh, I see. So, do you mean how do we got the observation?
Sort of like, let's say you have like two solutions, and you collect data from one solution and some data from another solution. Do you know, the classes of solution those data belong to, or
You don't know. Yeah, I think that's the main challenge. Yeah, you don't know.
right. Then how do you perform? How do you tackle this inverse problem if you don't know? Like you can mix them, right?
Yeah, you can. Yeah, I think I think the key point is in this loss function here. So you need to like when you let me think how to explain this. So you when you use neural network to approximate the solution, you take the minimum. So you select the neural network to approximate which observation is the closest one.
Oh,
Right. Okay. Let me annotate here. Let's say like you have, this is some data, and this is some other data. So let's say this is the true solution, and one true solution, this is another true solution. Then like I think there chances are, yeah, I will have something like this. Like, how do you prevent this from happening?
So here we have a minimum. So if okay. So for this question, I think because we have a PDE loss, so we can guarantee to some extent it is like a very smooth function. So of course you how to say so at the very beginning you have to yeah, that's a good question, and
I think this work is really impressive. So not only you're finding multiple solutions, in the end you categorize those data, right? So let's say those points they belong to one class, and those points they belong to another class. I think this is pretty expressive. And okay, so it's fine. So my last question is based on the information that you present about the MCMC approach. Have you ever tried the replica, like Langevin sampling methods for this kind of multiple solution scenarios? So I think they apply, right?
Yeah, so I think my advisor, Professor Guangling, actually has some works like to use replica exchange in applied mathematical field. So yeah, I think if you check his paper, he did a lot of work like to apply replica exchange to incorporate with DeepNet, and also to some kind of this problem. So maybe later I can send it to you if you are interested in.
Yeah, thank you. That's all my question. And excellent work.
But
thank you for the presentation.
Zheng, the question I have is, can we use the underdamped Langevin dynamics in the neural UQ library?
I think so.
Yeah, I think it should work.
Okay.
Yeah, well, we're basically like, I think George was talking about employing these sampling techniques for Bayesian neural network to solve PDEs. So that's what we're interested in.
Yeah, I think this is a very interesting topic. Yeah.
Because one of the methods we have is Langevin dynamics, so maybe the underdamped.
Right.
Yeah, I think this is very
other
promising.
Stuff.
Yeah. I'd like to talk about that if you are interested in later.
Yeah. I think George, we also talk about using sampling techniques to solve optimal control problems. And in optimal control problems, we have a lot of this, local modes, different modes. So maybe this type of sampling techniques, replica, how do you call it? Replica exchange, Langevin dynamics can be employed to discover multiple modes in open control problems as well.
Right, especially if you have the constraints, which are the boundaries, right?
Yeah.
Yeah.
Thank you, Haoyang. This is wonderful.
Thank you, Dorian. Yeah, good to see you.
Yeah, good to see you too.
Thank you so much, Haoyang. Do we have any other questions from the audience? It looks like we do not. Thank you so much, Haoyang, and thank you, Stefano. Both of you did a wonderful presentation today. With this, I think we can close this week's Crunch seminar. I hope you have a great week, and until next Friday.
Thank you so much.
Thanks.